Hi everyone. Today we are going to present our work Content Disentanglement for Semantically Consistent Synthetic to Real Domain Adaptation. The authors are Mert Keser, Artem Savkin, and Federico Tombari, and they are from Technical University of Munich. Autonomous vehicles employ machine learning techniques in order to understand surrounding environments. To get a reliable performance, the training set of these vehicles should cover different variations of environmental factors, such as lighting and weather conditions. The training set of these vehicles should also cover every traffic scenarios with near-accident scenarios as well. Collecting sufficient training data is hard, and the annotation is laborious and time-consuming. Synthetic data generation is a promising approach to overcome described problems. However, the recognition algorithms trained with synthetic data reveals a significant performance drop when the evaluation is done on real data. Generative-based domain adaptation methods have been applied to reduce the domain gap between real and synthetic data. These methods can produce visually appealing results, but the translation includes semantic inconsistencies. Many architectures have been addressed to solve this problem. The straightforward approach is to use auxiliary information such as semantic maps to track changes between source and target domain. Apart from the semantic annotation, the depth map could also be incorporated in the discrepancy measuring. In another work, pre-trained full convolutional network is employed to transform input images into feature maps. These feature maps are then used by the discriminator for discriminating source and target domains. On the bottom, you see an example of a translation of synthetic to real data. The network creates semantic inconsistencies by adding vegetations on the sky. In this work, we propose a new, unsupervised, end-to-end method that applies semantically consistent domain adaptation between synthetic and real traffic scene data. The training of the architecture does not require semantic segmentation maps or pre-trained networks. Our architecture is rather lightweight as it consists of a single encoder, a single decoder, and two discriminators. The lightweight architecture requires less training time and resource allocation. Therefore, it reduces energy consumption. Our pipeline consists of shared content encoder E and shared decoder G, plus one discriminator per each domain implied by adversarial L. As shown in the scheme, the encoder embeds the input sample XA or XB into latent code content A or content B. We enforce content to represent common features between the two domains, hence we call it content. The decoder G receives the code C together with one of the predefined domain-specific codes, style A or style B, in order to distinguish between two domains. We enforce two constraints in order to achieve the disentanglement. The first one is intra-domain reconstruction. XAA generated from content A and style A must be equivalent to XA. Reconstruction loss guarantees this reconstruction. The second one is inter-domain reconstruction. XABA generated from content AB and style A, where comes from XAB, shall equivalent to XA. Cyclic reconstruction loss ensures this reconstruction. Lastly, adversarial loss is applied to cross-domain images to match the target distribution. Here, some details on how three constraints are applied. The first constraint is reconstruction loss. The second constraint shows the cyclic reconstruction loss. And lastly, the third constraint shows the adversarial loss. The translation results of our method are shown here. First row and third row shows the examples from the synthetic data. Second row and fourth row are the translations of this synthetic data into real world with our method. Here, we want to highlight aspects of translation such as road texture, color of the lane marking as a quality of style transfer. Our method achieves visually appealing results with semantic consistencies. Here, each row demonstrates the original synthetic source image together with the images translated by respective baseline method. CycleGAN translates the car as a part of the road and also introduces vegetation-alike patches in the sky regions. Comparison with the M-Unit shows that M-Unit produces image-to-image translations in different styles due to its style sampling part. In the first example, M-Unit covers the whole sky with vegetation and struggles in keeping the semantic content unchanged. Similar to CycleGAN, M-Unit also translates the ego car as a part of the road. DRIT follows the design principles of M-Unit where both architectures disentangle input into shared latent vectors and domain-specific attribute vectors. DRIT struggles in consistency as well. CUT demonstrates that image-to-image translation can be performed by increasing the mutual information between the patches from the same regions of the source and translated images. The architecture uses the networks from CycleGAN and the implementation shares the same problems with CycleGAN in translation. CUT adds other artifacts such as in-painting of the car logo, which is typical for cityscapes datasets. Our method in turn shows consistency for all classes, especially vegetation, sky, road, and also ego car. Furthermore, we analyze the ability of our method to extract meaningful content vectors. We apply TSNE algorithm to the content vectors that is extracted during the 200 epoch of the training. In the left figure, red boxes shows the content A and the red boxes with cross shows the content AB. In the same time, blue boxes shows the content B and the blue boxes with cross shows the content BA. The figure shows that content codes extracted from source images match with the content codes extracted from cross-domain translated images. Therefore, content A match with content AB and content B match with content BA. In the right figure, the interpolation results of content vector with source and target styles are shown. On the top, content vector is combined with the source style, and on the bottom, content vector is combined with the target style. It confirms that the disentanglement of content and style codes. For quantitative evaluation, we train semantic predictor network on the dataset generated by translation of GTA images to cityscapes. The first row of the table shows the performance of the segmentation algorithm when it is trained the cityscapes train and tested with the cityscapes validation. It represents the oracle and the upper bound. The second row shows the result when the segmentation algorithm is trained with the PFT dataset and tested also cityscapes validation. Other rows shows translation performance of the CycleGAN, DRIT, M-Unit, and CUT. Here, one can see that our method improves segmentation accuracy by 2.9 points, achieving 88.7, and mean intersection over union measure by 1.6 points, achieving 39.0. Our method also shows improved performance for multiple classes, such as building, vegetation, sky, car, and so on. In this paper, we propose an unsupervised method for semantically consistent synthetic-to-real domain adaptation of urban traffic scenes. We compared our method with state-of-the-art networks in synthetic-to-real image translation. Visual and quantitative comparisons on synthetic-to-real image translation show that our architecture improves the visual quality of translated images as well as the performance of deep semantic segmentation network on the translated images.